My name is Brian Agee. I am a PhD candidate at Tennessee Technological University in Cookeville, Tennessee, and my research advisor is Dr. Dan Swartling. The research that I'm currently involved in concentrates on trying to develop a means to eliminate electrical use in synthetic organic reactions. Main purpose in doing this, it takes fossil fuels in order to use electricity. We're becoming depleted in fossil fuels. Furthermore, approximately 1.8 billion people worldwide live without electricity. So things that we are currently doing, some people in some parts of the world do not have the capabilities to do those. So in order to do this, we first developed a solar reflector seen here on the screen, which consists of an unused satellite dish, just a typical Dish Network DirecTV satellite dish, in which we've covered with a reflective mylar tape. Same principles as if the satellite signal was hitting the dish applies here. Sunlight hits the dish and is reflected off of the dish to the position where the feed horn on the dish is located. Because of this, what we did was cut the feed horn off and then insert a material in order to hold glassware in place at that point. When we do this, the sunlight is then reflected off of the dish and is reflected onto the bottom in a direct focal beam to the bottom of whatever we're heating. Well, light's going to pass through just typical glassware, so in order to compensate for this, the bottoms of all the glassware that we are reacting solutions in are painted black with engine block paint, which is a high temperature paint which is not going to melt off. So now sunlight hits the dish, it's reflected onto the bottom of the flask, and the solution begins to heat just as if you were heating it with electricity inside of a laboratory. So to test this out, we first looked at several different solvent systems, everything from water to high temperature boiling glycol solvents. For instance, when we set the boiling point test up for water, we were able to achieve water boiling at 100 degrees Celsius in 30 seconds. Diethylene glycol, which boils at around 236, we're able to achieve boiling of that solvent within 3 minutes, using only solar radiation as the heat source for this. So seeing the results that we saw from this test, we then assumed that, well, chemical reactions were a viable options for the setup that we're currently employing. So we tested several different reactions using the solar reflector heat source. We looked at Friedel-Crafts reactions, Wolff-Kishner reactions, Diels-Alder reactions, Fischer esterifications as well, all which are pretty high boiling temperature reactions. We then did a comparative study in which we looked at how the yields for each reaction worked, both using solar radiation as the heat source and then electrical source as the heat. And we found that we saw comparable yields for both cases. So the solar radiation as the heat source is a viable option. The yields did not decrease, and actually in some cases we saw increase in percentage yields. Furthermore, we've also, besides chemical reactions, we've also performed simple distillation using this as well. The ester products that were formed from the Fischer esterifications were able to distill using a simple distillation setup. So in conclusion, we have successfully developed a device in which we can thermally heat synthetic reactions equivalent to using electricity. Seasonal variations do not seem to be a problem. So if you noticed in the first picture that I was demonstrating, there was snow in the background. We're able to get these reactions to work during all 4 seasonal periods, even when snow is on the ground. In future studies for this, we're currently looking at scaling up the procedure to see how this model would actually work in an industry type setting, so much larger scales. We're also looking at seeing how we can work on doing a complete total synthesis of a multi-step synthetic reaction of commercially important products as well. If you would like further information on our work, you can contact either me or my research advisors at the email address seen here.